Yes, so Avi gave me 4 hours, which means I'm going to take it very leisurely, or maybe painfully. I don't know for how it will come out. My goal is to make the first hour an introduction to homology theory. So I think for some of you this will be a little boring, but you're welcome to go and return in the second hour. So for those who
know it, or for those who don't?
No. For those who know it can. the other have to stay. High-dimensional expanders. So by now there are a lot of different approaches to this idea, and I'm only showing to you one of them. Others, there is one by Avi and Friedman, and there is an approach due to Gromov, and there is an approach due to Lineal and Meshulam. And and it is not clear at this point what is the relations, what are all the relations between these approaches, what is an expander according to one approach, what does it say about other aspects. My approach comes from topology, and I should say that things I will show you are based on a lot of joint work with Ron Rosenthal, Ran Tesler, Konstantin Golubev, all of them students in the Hebrew University. And the idea is the following. We start with topology. So for a graph, this will be the idea of connectedness. So everything I'm going to do is going to be somehow parallel, analog to what people should know in graph, but I will also tell about the graphic pictures. Then we have a quantitative. This topology is something of a qualitative aspect. So is a graph connected or disconnected? Then we have geometry, which can be thought of as a qualitative measure of things we see here. Here it's the spectrum of the, let's say, Laplacian spectrum, which also tells us about connectedness, but now in a quantitative way. And then we want to take it to combinatorics. So here, for graphs, it will be the Chigger constant or pseudo randomness. And so I also tell a little about what happens in graph, but our goal is to do this in higher dimensions. So I'm starting with graph, but not with the usual point of view. I'm going to define first this space omega, which is the space of flows. So we have a graph G with vertices and edges, and flows are assignment of directed values to the edges. So if this is my graph, a flow is something like I say, okay, here 3 goes in this direction, here 2 goes in this direction, 5 here. I can say -7 in this direction, and this is the same as the same thing, but 7 on this direction. So, and here you can put -3 and 2 again. So it's an assignment of values, but I can flip the direction and flip the sign. But I should say, and I will say it a lot of times during the lecture, I don't choose at any point direction for the edges. The edges are not directed. A flow is just an assignment of directed values to the edges. Okay, so this is
But there is no conservation. It's just
no,
function.
no, any function, yes. So the dimension of omega is the number of edges. I need to assign to every edge. But unlike, for example, function on the vertices, I don't have a canonical choice of basis. And this makes it a little bit harder to work with. So no canonic base. So I do get bases if I choose. Now, if I will choose an orientation for the edges, I will get some base, but it's not canonical in any sense. So it's not. Usually, you don't want to do this if you can avoid it. Now, for a flow, you have the boundary of the flow. So the boundary of a flow, the boundary is a linear map from the flows to functions on the vertices. And the boundary of a flow, which looks like this, so if I have one going like this, it's the function which is -1 here and 1 here. So it's a function on the vertices, and you think about this as if this flow is taking one from here to here, this will be the effect of this flow. And what can I say using flows about the graph? So remember that we're interested in connectedness.
So just a second. And this is extended linearly. You define it for an edge, and you
Yes,
extend
yes,
this
yes.
delta is
Yes. So yeah, let's take another example. If I do something like 2 and 5, then this will be -5 here, -2, and 7 here. It shouldn't be, no, but in general, you usually have more edges than vertices, so you don't expect. But you can start thinking what happens in a tree. And so what I want to ask is related to your question. When do I...
Circulations, for example, will always map to 0.
We're taking it slowly.
No, I'm just answering Or's question a bit, but
Yeah.
go on.
So let's say I have a function on the vertices. When is this function the boundary of some flow? So let's take this and put here 1, 0, 0. Can you build a flow whose boundary is this function? Rotem. I saw you not. Okay. Why? You have to put here 1, right, to get this one here. But then you're taking 1 away from here, so you'll have to put 1 going here to compensate for it. But then here you'll get -1. So you don't get this 0. So you see that you have a global obstruction here, which is firstly only if the global sum is 0 when I go over all the vertices. Because a flow only moves, think about it as quantities, it only moves something, 1 from here to here, but it preserves the global sum. So first of all, I'm not expecting to have a function as a boundary of a flow if it's not of sum 0. Is this the only obstruction? Good. So if I have something like, well, first of all, it's nice also to think about functions of this form. Put 1 here and -1 here. And it's nice to think about the form whose boundary of this. If you take a path, then all the values along the path cancel, and you get 1 and -1. Okay, it would be the other way. -1 from here to here. But if you start with a disconnected graph, and I put 1 here and -1 here, I can't have a flow whose boundary is this function. So intuitively, I think it's clear that I need to take this one. I'm taking one from here, but I'm only moving it inside this component. So we encode these two obstructions in an algebraic way. We have a function on the vertices. We have the flows. We have here the boundary map, which takes the flow to 5, 2. So this is the boundary map. It takes it to -2, -5, 7. And here I'm adding a new map going to the reals. And this map is taking any function, so 2, 3, 4, to the sum. So in general, f goes to the sum over the vertices. And this is also called a boundary map. So to distinguish between them, let's say that this is the zeroth boundary and this is the first boundary map. And what we just said is that we always have, if I start with a flow, then delta f, the boundary of a flow is always in the kernel of the zero boundary map. Everything which comes from a flow gives you a function with some 0. So the image, so this is del 1. So the image of del 1 is inside the kernel of del 0. And we want to say when is this equality? When is the image exactly the kernel? So when do we know also that any function which sum to 0 comes from a flow? So we just said there is an obstruction for this, which is the connectedness, and this is the answer. So this is if and only if G is connected. So it's maybe you see the proof, but I want to spell it out because it has some analog later in higher dimension. How do you see this? So we saw it's an obstruction, but now I want to say that this is the only obstruction. If the graph is connected, then any function with sum to 0 is the boundary of a flow. I'm open to ideas. You're ahead of us. This is what we will do in higher dimension. Here, it's more simple. We take a vertex. We take a vertex, and now for all the other vertices, I look at the function which is 1 here, and then -1 here, 1 here, -1 here, 1, -1 here. Yeah, I don't need another one. For each one of these, we saw that because it's connected, I can find a flow going from this to this, and the boundary of this flow. And it's not unique. I could go from here to here along this way. But these flows connect, taking paths from a fixed vertex to all the others, give me vectors of this form. And we know that these span the function of sum 0. So this is linear algebra. So I tried to give this talk to my wife yesterday because I said this is super elementary, but at this point I understand that, yeah, you have to know something about linear algebra. So we have one constraint, and therefore n-1 independent vectors span.
You can explain this out algebra. You just add greedily vectors until you get to the flow you want.
That's true.
You should try
I'll try it. I will do that also. Okay, so we have this. So we have this if and only if it's connected, but there's more to it. In fact, we see the amount of connectedness. So the dimension of the kernel minus the dimension of the image. So this is a subspace, and I have also a quantitative measure, how far they are apart, what is the difference in dimensions. And this tells me the number of connected components, -1, right? If it's connected, then these are equal, and I get here 0. How do you see this? So this is, we set the function with sum 0 over all the vertices. But what is this? What is the image of del 1? Exactly. So this is some function which sum to 0 on every connected component. The way to see it is this, actually. You can see that I can do this for every connected component. I can span all the function which sum to 0 on this connected component. And if you're comfortable with quotient, then the quotient space has a name. This is called the zeroth homology. And we see that the dimension of the zeroth homology is, okay, let's not talk about dimension. Let's talk about the space itself. The zero homology is just R to the number of connected components -1. So the zeroth homology tells us the number of connected components. But this is not the way I want to understand connectedness from flows. There is another thing I can do, which is take a function on the vertices and define a flow from it, going the other way. So I have here a function. Now it's 3 -2, 7. No. And the function I'm looking at is the differences. So differences between values over the vertices are naturally flows. They are naturally directed values. So this will give me the flow 5 here, the difference between 2 and 7, and also 5 here. And this map is dual to this map, so we will write it del 1 star, and we call it the co-boundary. This is the boundary map. And this is the co-boundary. So what do we mean by dual? If you remember what you did in linear algebra 1, then you'd think about the dual as the transpose of a matrix. But in order to have a matrix, I need to choose bases. And I don't want to choose bases. But if you remember also what you did in linear algebra 2, then you should remember that dual is something which satisfies this. That if I for all f and g. So note here that f is in a function on the vertices and g is a flow. So you can work it out like this without resorting to choosing a direction, but okay, at this point I allow you to choose a basis and convince yourself that this is the dual. So let's think what happens if I choose a basis. Then here I get a matrix. The boundary is a matrix which is indexed from above by edges and here by vertices. And because the edges are now oriented for the choice of a basis, every edge has an origin and a terminal, and we get 1 and -1, maybe the other way.
I'm sorry, how do you define the co-boundary again?
Wait, so this is still the boundary.
Oh.
You can think about it without bases, and then you have a function on the vertices, just write the differences. So here, this is bigger by 5 than this.
You should emphasize the pairing.
The pairing.
I think you should emphasize that, otherwise.
No, but first of all,
I mean, here you have a path. So
I want to give a definition which doesn't even say that this is the dual of this.
Doesn't matter if you have a path. You just, for every edge, you subtract the values on the vertices and directly.
right.
Yeah, the 3 here wasn't so good. I should have taken 4, and then this is bigger by 6. So this is bigger by 6 than this. This is bigger by 5 than this. I just write this. But I could define it like this without any reference to the boundary. But it is coming from the boundary.
In that example, the values at the vertices don't come up to 0, right?
Here,
Yeah.
no. No, here these are all the functions on the vertices. Yes. It's not that I take a function which comes from here. I take now any function and define from it a flow. And the flow is just, think about it as the derivative. What is the change in the, or the gradient, if you like this language. This is the gradient of this function. What is the change as I go from one vertex to another? When I travel this, I gain 6. So right here, 6. But it's also the adjoint, the dual of the boundary map. So if I would choose a basis here, then I would get here for every edge 1 and -1 according to the orientation I choose. And here it would be the transpose map. So it will be here. Now the edges will be here, and you would put here the origin and the terminus, and you will get this map. But I don't like this, so I'm going to, I said it because it gives you a concrete way of computing things. You can now implement this in software and compute everything, but it really clutters up the intuition and the proof when you start choosing bases. So we don't want to do this. And this is a way to do it basisless, but it also, I think, you need to work a little to see that, you need to think about it to see that this is exactly the dual of this. Perhaps I didn't say at any point, but the inner products are exactly what you expected them to be. So FF is V, and if I have two flows, then the inner product is G along all the edges. And now something does happen. I don't need to choose orientation for the edge because I'm multiplying here too. So if instead of taking E in this direction, I would take E in this direction, I would get minus here, and they cancel. So I have a little magic here which makes this the inner product definable even if I didn't choose a basis. Yeah, I didn't define it, formally in the sense of if I would need to put it in a lecture note. So this is really how I would define it at the end. But I wanted to give it very graphically. Yeah, but if you at the end of the day want to write this, you will say that it's assigning of values to both directions, such that if you flip, you get minus the value. Okay, so we have this dual, and let's see what happens here. So this is a matrix is very clear. This is the matrix 1, 1, 1, 1, 1, 1. It summed all the values of the vertices. Here also, there's not canonical choice of base because you do have to choose an order for the vertices. You don't think about it a lot, but you still have some degree of freedom here, but it will always look like this. And the dual is this map. This is the zero coboundary map. And it takes, what this does is takes a value and takes it to the constant function. So I have here 7, it goes here to the function 7, 7, 7. And again, you see that if you start with a constant, you take its coboundary, and then takes its coboundary, then this is the constant function, and the gradient, the change along vertices, is 0. So again, anything which comes from here goes to 0 here. So we have the image of the 0 coboundary is again contained in the kernel of the first coboundary. So here I gave you a straight argument, but you can also just observe that if I take them consecutively, then this is the same as doing this, right? You know that transpose flips the order, and we already said that this is 0. So this is the dual of 0, which is 0. So since you can see it directly, this is not very insightful, but it will, because it's a good argument to have on higher dimension when we don't see everything very clearly. So, and again, I want to understand when is this equality. So what do we have here? What are these spaces? This is easy. These are the constant. Right? Everything which comes from the co-boundary of a scalar. What is this? Why?
So when you're connecting components, if you want all differences to be 0, then you can run your filter.
Exactly. So this is the co-boundary gives to every edge the difference along its edge. And being in the kernel means that the difference along every edge is 0. So the original function along every edge has equal values at the extremities of every edge. So this means that it is constant. So I will say this is locally constant. Constant on every connected component. And when is this equality? When is a locally constant function necessarily constant? Again, when G is connected. And again, if we look at let's look already at the quotient, at the kernel of, look at locally constant functions, modulo constant functions. So locally const, modulo const, then, and this is called the zeroth cohomology. I didn't write the name, but so this is the zeroth homology. And this is the zeroth cohomology. So the dimension of locally constant functions is the number of connected components, right? I need to choose what value I give to every connected component, but I subtract one because you can think about it, I'm modding out by the constant, or you can think I'm working orthogonal to the constant. It gives me one constraint, and again I get here that this is R to the number of connected component minus 1, like we had here. So, but this is a bit misleading. So first of all, we worked here on simplicial complexes. But now think if we try to do this for general topological spaces, then here the question was, is a locally constant function necessarily constant, which is what we get for connected spaces. Here the question was, can I build a path between any 2 points, which is path connectedness. It's not exactly the same. Also, in topological settings, you could get different things here. And when we go to higher dimension, there will be much more difference between homology and cohomology. Here it was, the question is, I wanted to understand when the cohomology is trivial. And this is, when is every locally constant function constant?
Oh,
But here it was, here it was, okay, here it was some zero, so this is, I can define it like this, but it came from the question, can I build a path between any 2 points?
Doesn't duality have to make the dimensions the same?
For fields.
For fields, you mean the values are common?
If because I worked over R, it will be the same. If you do it everything with integral functions, so all the values would be integers, it stops being the same.
Yeah, okay, but for fields it's the same. I mean, it's just duality. Transpose the matrices should affect that.
Yeah, yeah.
And in fact, these quotients would be isomorphic.
Isomorphic, but you know, not naturally.
This inner product is not that's why I think you should highlight the inner product.
Mm-hmm.
Geometrically,
Yes.
these are the issues. What's your inner product? What's the covariant derivative?
That's true. This inner product seems very natural, but I could change it arbitrarily. I could put here some scalars for every vertex. I could make it weighted, and still everything would work, and duality would work. But the homology and homology are isomorphic, but not naturally. And also, when you look at them as functors, they go in the other way. One of them flips the directions of maps.
It used to be, in the old days, if anybody was in Princeton, the first thing they learned is cosmology. I guess that was a change. So can you say, I mean, is there is one in some sense better than the other? I mean, it seems like, I don't know, number theory, algebraic geometry, it seems like homology is much more,
So
at least visible.
topology.
So is there a reason for it?
So topology is like cohomology because it has a ring structure. There is product between cohomology elements, and the dual notion is less useful. But as Peter said, this is a huge subject, and I think I'm not the expert. But we will be more interested in cohomology for what I'm aiming at. I don't know, a lot of time cohomology becomes more useful if you have some insight. Ring structure. But we're not going there also. This is not the reason I'm looking at this. Okay, so this is topology, and now we move on to geometry. So for people who come from differential geometry, it's very obvious that if you have this differential and codifferential, you compose them. But even if not, so let's do it. We have the Laplacian, which is going up and then going back down. So it goes from functions on the vertices back to themselves. I'm going high up. I construct the flow corresponding to a function and go back to the co-boundary. So let's do one example. If I have here these 2, 3, no, let's do it ABC. Then first of all, I need to apply the co-boundary, and then this would be, let's say, A minus B to here, and C minus B. And then the co-boundary will take A minus B here and minus here. So this will be A minus B. This will be C minus B. And this one gets both of them. So it gets, and with minus because it's the origin. So it gets minus A plus B, and here minus C plus B. In total, 2B minus A minus C. So if you follow this, you should believe me that the Laplacian give you the original value times the number of neighbors minus your neighbors. It should be obvious here. And
Can you say a few words about why it's a natural thing to do?
I didn't say it's natural. I said it would be natural for people who come from Riemannian geometry because this is like the thing they study for centuries. But no, you also have. I mean, I think if you talk to a physicist and really use this intuition of gradient and the dual is the divergent, he can give you a nice intuition why the composition gives you some measure of change, right? This tells me how much a function change around a value. I think you can work it out, but I don't. I never.
Something called Hodge theory. The Hodge theorem computes homology using the zero kernel of this self-adjoint operator on one space. Now this goes from one space back into itself. And I think the Hodge theorem is
It tells you this, but I don't see the geometric intuition, the clear geometric picture there. But I'm aiming to Hodge. So we are interested in the spectrum of the Laplacian, but we have one trivial value in the spectrum because we know that. So the Laplacian is let's put it in this picture. It's going here and then back. So this is the Laplacian. And we know that everything which comes from the constant is going to vanish when I take it one dimension higher. So if I take the Laplacian over the constant, then this is 0, right? This is del 1 and del 1 dual, del 0 dual, but this is 0. So this is 0. So, and this 0 is not very interested. I know I don't need to look at the graph to know that I will have this 0 in the spectrum. It comes from the algebra. So, and I think you say, okay, well, it's obvious that this function takes constant, this operator takes constant function to 0. Why do I need to look at the dual and codual and do this? The reason is that in high dimension you won't have this easy intuition why. So don't translate things to what you're familiar with from graphs. Try to look at the weird notation I'm using. And so what we want to do is look at the spectrum of the Laplacian, but restrict to the orthogonal complement. So the orthogonal complement of what's coming from below. And now we have the fundamental theorem of linear algebra, I like to say it, is that the dual, the orthogonal complement of a dual is the kernel. So this is just the kernel of del 0. Now, take a moment to translate it to your language. I've just said here that the dual of the complement of the constant are the function which sum to 0, which is completely obvious. But again, in high dimension, we won't have this obvious interpretation. So let's call this the spectrum of the graph. So the spectrum of the graph is a spectrum of the 0 Laplacian, but restricted to function of sum 0. And now we get to Hodge. When is 0 in the spectrum of the graph? And here is another useful fact from linear algebra. The spectrum of the Laplacian, this is the spectrum of going right up and then down. Oh, sorry, I want the kernel. And the kernel of a dual, of the composition of a map and its dual, is just the kernel of the first one. So do you know this guy? It's one way is obvious. Everything which this kills, also this kills. For the other one, if I have a del 1 star, if this is 0, then also multiplying it by every other function is 0. And then by duality, then this is del 1 f, and here del, okay, I could take here just the f, it would be easier, and then I get here del 1 f. So, and the inner product is 0, but this is an inner product, so this means that this is 0. So this is the argument. This is also something which will fail if you're not working over the reals. If you're working on the finite field, then this fails completely. And so 0 in the spectrum, it means that we have something in the kernel of del 1, but now we need concentration. We're only looking at the spectrum restricted to the orthogonal complement of the image of what's coming from below. So we really ask here, so this is the same as having kernel of del 1 intersecting non-trivially the orthogonal complement, or let's say just being bigger, so being strictly bigger than the image, right? The kernel of the spectrum is, the kernel of the Laplacian is the kernel of the co-boundary. We're not looking at what comes from the image, we're looking at the orthogonal complement, so we want to know if there is more. And this is exactly first zero homology, different from 0. So when G is disconnected. And again, you can think about the Laplacian and say, okay, yeah, if the graph is disconnected, then I can construct a locally constant function which sums to 0, and this will be there. This will be this non-trivial kernel, but it won't help you in high dimension. So this is the geometric picture, and now the idea is to take this to topology. So this is Hodge, I think. I think what happens here is, as Peter pointed out, this is Hodge, saying that the spectrum of the Laplace operator tells you about the homology, the cohomology of the space. And geometry is, and combinatorics comes from somehow quantitative geometry. So we have, if 0 is in the spectrum, it means that the G is disconnected. So we want to say that if the spectrum is not only not containing 0, but also far from 0, then G should be very connected. Right? If the spectrum doesn't contain 0, then the graph is connected. So we want to have now something quantitative. And we have that. We have the Chigger inequality, which tells us that if the spectrum of the graph is far away from 0, then you have large connectedness in sense of large Chigger constant. I'm not going to do this for graphs. I'm going to show now the analog for higher dimension. So we're moving up. So now we have a triangle complex. So it has vertices, edges, and triangles. And I also look now at triangle flows. Triangles. So E is just some collection of pairs of vertices, and T is some collection of triplets of vertices. And now I should say if I have some triangle. What? Yeah, a triangle two complex. And if T is in the complex, so if some triangle ABC is in T, then I will need to have all the edges AB, AC, and BC in the edges. So this is one restriction. You have to build this theory.
In the same way that different edges in a graph, then its
You-
breakpoints are vertices.
Yes, but somehow it's not obvious because you could do this without this restriction, and then you would just say that you're studying hypergraphs. You wouldn't say complexes.
Yeah, but in complexes.
Yes. Yeah. So if I have a triangle, I need all its edges. For the following reason, I'm defining now the space of triangle flows. So let's call these edge flows. And now we have triangle flows. And
Is there any reason you call it omega E and not? I mean, these flows are just functions. So
no, they're not functions. I mean, they're functions with some constraint.
It's like
So-
how to the 2E mod of this equation.
Yes.
Quantity is this
But-
minus this.
But it is, yeah, it's a subspace for which you don't have. Omega comes from differential geometry. This is how they look at forms, and really it's a good intuition. This is something I learned from. I learned it a few years ago. What?
a very good teacher.
A very good teacher. Yeah, that it was in a conference a few years ago, and someone said that whenever you have functions on edges of the graphs, try to think about them as differential forms. And it was it stayed with me, this idea. And it really behaved like I said, the gradient. This is not a function; it's really a directed function, like a gradient. Okay, so what is a triangle flow? It's assigning, I have now triangle, and I'm assigning, again, values to direction. So now direction is either clockwise or counterclockwise, and again, writing this is this triangle flow is the same as -3 in the other direction. So again, it's I could say I assign values to both directions, but I put the constraint that they're opposite. And I have the boundary map. So the boundary map is, if I have here, say, 7, the boundary of this is 7, 7, 7. And then you continue linearly. So if I have another one here with, let's say, 2, going like this, then this will be 2, 2, and here 9, because they both go that way. So this is the co-boundary map. And okay, now we have already 3 co-boundary maps. We have del 2, del 1, and del 0, and I defined each of one separately, but the general definition is that if you have some cell which is of cell with I vertices, and I want to understand what goes on, I'm adding all the vertices I can. I'm looking at all the vertices such that if I add them to the cell,
These are vertices or these are one lower dimensional?
V are vertices and sigma is one lower. But V is a vertex. So I look at the way I can add a vertex so that this is still in the complex, and look at the value there. So this will be the general boundary map. This is why I allow myself to call all of them. So here it's I have the empty set, and I ask, how can I add a vertex and get a vertex? I can add any vertex and get a vertex. Here I have a vertex, and I ask, how can I add a vertex and get an edge? And this means that I need to add a neighbor. And here I have an edge, and I ask, where can I get how can I add a vertex and get a triangle? These are the neighboring triangle to this edge. And the dual one would be the coboundary map, which takes So if I have here some A, B, C, this takes it to A plus B plus C. So summing along the boundary.
But in this definition, if we look at delta 1, how do we get that some, if you have an edge, then one vertex that has, say, 1 on it, one vertex becomes minus 1 and the other 1?
So it would be, I want to understand what happens. So this is for a vertex, right? I look at a vertex, and then it means that I look at all the W which are adjacent to it, and I look at VW. But the direction here is important. It's V going to W. So it would mean that if my functions look like this, here is V, here is one W, here's another W, I measure them going like this, all of them. So when I put examples, I always put an arrow in the positive definition, in the positive direction. But here it will not be positive.
I see.
Yeah.
This is a bit misleading because you have all the permutations.
No, I'm not assigning values to all the permutations.
But, when you add something, it doesn't have to be in.
It depends on the sign of permutation.
Oh, yeah. Just okay, you're right. Maybe I shouldn't have said this. That to make this precise, I need to say that I also allowing to make even permutations without changing the values. Yes.
Even in the odd permutation.
Yes. So let's not go there. I wanted to show that I've defined a lot of maps here. So I wanted to show that I'm not defining a lot of things. There's one definition which gives everything at once. But yeah, I'm not. I want to. The nice thing that as long as you work with vertices, edges, and triangles, you can still do everything graphically. You don't have to go into permutations. You really can see the directions.
So maybe this is what you're trying to avoid, but is the full definition does it involve antisymmetric objects?
So yes, this is what I would call antisymmetric object.
Like antisymmetric tensors? Or forms?
This is like the discrete analog. We like to think about these as the discrete analogues of tensors. So this would be functions, but this will already be vector fields and then two tensors. But this is like an intuition. It's not something formal. Okay, so this is a boundary map and co-boundary map. And at what point to take a break?
If you wish, but yeah, I guess it's good. Yeah. So you decided 5 of them.
Because now we're going to do a little harder. I think I want people concentrated.
Did your wife take a break?
If you return, yeah, we lock the door and then we'll take a break. So let's take 5, 10 minutes.
So you are the boss.
8. Okay.
You concentrating on 2 complexes because the theorem you're going to describe is only for 2 complexes?
No. But then then I'll need to resort to permutations, and I don't want to do that. And but the proofs are not different. So, I mean, if you see what happened, if you understand 2 complexes, I think you understand the general picture usually. Okay, so now we are here, and we want to understand what happens in edges. So before we look at triangle even, let's look, we still didn't look at what happens at the downgoing map. So I'm interested now in the kernel of the first coboundary. So so this is the analog of the sum 0 functions. Right now we shift everything we did 1 dimension higher. So the kernel of the 0 boundary map is the function with sum to 0. I want to understand what is the analog of that 1 dimension higher.
These are the flows.
Yes. So what is the kernel of del 1? So let's.
I mean, circulations.
Okay. So it means that I look at the differential of a flow, yes, and at every vertex I need to get 0. And this is the sum of outgoing edges. So all the edges which go out of the vertex. Right? This is what O ask how do I see the 1 and minus 1, and the answer is that when I look at the vertex, I look at the outgoing edges. And sometimes the value is positive and sometimes it's negative. So this is what I like to call it Kirchhoff.
It's only one of the Kirchhoff laws, that's it.
I think we, okay.
Combinatorial is called circulation.
Circulation?
Yes.
I didn't have this one.
Some it has with vertex
I also.
The flow is not going anywhere, it circles around.
I also heard current.
Well, current can be between plus and minus.
Oh, you have like
like
power source.
voltage, it is your power.
So let's not do that.
You can also decompose it into cycles like so.
There. Wait.
Okay, just a second. I mean, Kirchhoff is just the kernel of theta 1?
Yeah, exactly. It's what happens. I mean that if I have here like some 5 going from this way, the co-boundary sums from all the neighbors. So it means that I must have 5 entering here, and then the co-boundary will be 0 here. And let's say I have here this, for the same reason 5 is going out, so I need 5 going in to make the boundary 0 here. And now this is 5. Maybe now I have. I mean, it can be more interesting. It could be 3 going here, 2 here, and 2 here. This is still Kirchhoff. See here, 3 is going out, 2 is going out, 5 entering. But it has to be locally preserving. So everything which enter a vertex is coming out of it. So this is the analog of sum 0. And now, and this is not very useful somehow for our purposes. I want to show you that this is also, I think this is what you mean, that it can be decomposed. So this is also the span of cycles. So what I mean by cycles, I have here some graph, and cycle is just a closed loop. So I put 1 along the closed loop, 0 everywhere else. A cycle is definitely Kirchhoff, because every one which enters somewhere exits, and everywhere else there is 0. So obviously also the linear span is Kirchhoff. So we have this, but I claim that also the other way. If you have a Kirchhoff function, then it's a sum of cycles.
Only cycles with edges in E, or
Yes, yes, yes. You cannot have. You cannot step into the void. No,
you have
no,
the cycle space of
no.
the graph. He's talking still about graphs, not
Yeah. So yeah, this is actually I don't need the triangles to do what we're doing now. When we add triangles, when we'll add triangle, we'll be interested whether this cycle bounds triangles or not, but we're still not there. So why is every Kirchhoff function a span of a cycle? Here, this is what I think you were thinking at the beginning.
You take the smallest value and you find the path for it, and you subtract.
This is not how I think about it.
But you agree that
Interesting.
it
What?
works. You agree that it works.
I don't see it. No.
If you had an arbitrary circulation, arbitrary Kirchhoff function, take the smallest non-zero value, and follow it. I mean, since it enters somewhere, it leaves, and you close the cycle.
Okay, you start the like the Euler.
You subtract it one.
So yeah, it works. But the argument I came up with, I think, is nicer because it shows you some things. And I mean, it's not I was the first to come up with this argument or something. Actually, I think Eddie came up with this argument. I think it was your argument. I'm sorry, it's not even. I even didn't come up with it. So the idea is pick a spanning tree. So here is a spanning tree for this graph. And now, for every edge outside the spanning tree, close it to a cycle within the graph. So for this edge, I look at this cycle and put some direction, doesn't matter. So I have here one cycle, and here is the second cycle going 1, 1, 1, 1. And I claim that already these cycles, which correspond to edges going outside the tree, they already span all the Kirchhoff functions. And the idea is that if I have any Kirchhoff function, I can kill the value here and here by these using these cycles. So I can add some value of this cycle to make this 0, and then some value of the other cycle to make this 0. But the original function was Kirchhoff, and I added cycles, which are in Kirchhoff. And Kirchhoff is linear, so I still have a Kirchhoff function. But now this is a Kirchhoff function supported on a tree. And this is 0 because pick a leaf, Kirchhoff means that the edge next to it is 0. So delete it from the tree. Now pick another leaf, do it again and again, it's 0 everywhere. So I think it's not very different, but still you see here somehow, I think this is somehow analog to the argument we had for graphs to show that the functions of sum 0 are the ones which come from above, and we had to pick a vertex and choose passes from it. And here we chose a spanning tree. And it's somehow this choice of a basis, generalized, like in one dimension higher, turns into a choice of spanning tree. And I'm just saying it because there is a work of Gil Kalai about counting the higher dimensional analog of trees, and it starts from there. It's like instead of choices of a base point for a graph, you need to choose a spanning tree for your complex. I think you get a hint for it here. Okay, so this is the span of cycles.
And by the way, you could also view Avi's argument as a generalization of what happens in the case when you want to argue that if a graph is connected, then
Yeah, because I can take values and make it 0 by pushing it.
There you could just pick paths and make and subtract them greedily, and here you take cycles and subtract them greedily.
Yep, you're right. Okay. So this is the kernel, and what is the first? So we want to understand what is the higher dimensional or analog of connectedness. What is homology and cohomology? So the first homology is the kernel of del 1 modulo the image of del 2. So we already said that this is Kirchhoff. What is the image of del 2? So now I have also triangle, otherwise this is very boring. So if you don't have triangles, by the way, the first homology of a graph is really the cycles, the number of independent cycles. But now I have also triangles. So let's say I have this triangle, I have this triangle. Here I don't have a triangle. So in the image, the image is the span of the boundary of triangles for all the triangles in my complex. So I don't have anything clever to say about this. I'm sorry. But the thing is, the span of one triangle is a cycle. So if I take this, I get this cycle. And since I have span, there is something which is important to say here. Since I have span, I can also look at the span of at the boundary of one triangle plus plus the boundary of another triangle. So here, if I take this triangle and orient it like this, then at the boundary, this edge will cancel because now this goes like this, and like this.
Yeah,
So
that they have the same value in the triangle.
yes, the two values.
1 and 1.
Yes. So in the boundary of this triangle plus the boundary of this triangle, because I have the span, in total I got this cycle. So when you think about, you look at this, you think, okay, you don't get any cycles, you get only cycles which are of length 3, but no, you can start summing these and get longer cycles. So you really should think about when you have some part of your complex which is divided into triangles, you can always take the sum of the triangles and get the cycles which surrounds this. So the first homology is the Kirchhoff. I don't want Kirchhoff. I want to say cycles in terms of loops. But I don't want to look at loops which I'm modding out loops which are boundaries of surfaces. So these are boundaries.
What I've asked is if you have to take triangles with 1, 1, 1, and I don't think you have to do it.
No, if you don't do it, you will not get cancellation of the edge.
But if you don't, this way you only get boundaries which have 1 on every edge, and I don't think that's what you only want to get.
So everything is
No, I mean, you do want to get, we want to get functions which are sums of constants on cycles, but at the top you get all cycles.
but here it's
Circulations are exactly the linear combination of constant functions on cycles, on directed cycles. And at the bottom you get the same, only restricted to those cycles that bound the triangulation.
so it's true, but it's not obvious because maybe there are 2 cycles, and I can't get neither of them from as a boundary, but maybe some combination of them is a boundary. So it doesn't happen, but I mean, you have to.
Sorry, what is not obvious?
I'm trying to give you exactly the intuition that you said. That here, these are all the cycles, but I'm modding out by cycles which are boundaries. And if you only look at cycles, then maybe you have 2 cycles, 2 independent cycles, which are not boundaries, but there's some which is not cancelled, which is not a cycle anymore.
All you will need to do is to prove that the boundaries are all the image.
Are all there?
The image is exactly spanned by.
Yes. So this is for the homology to be trivial.
No. For the homology to be trivial, then
I need every.
Yes, then you need to get everywhere. But forget triviality. I mean, the image of delta 2 is exactly all cycles that can be that are bounding a triangulation.
It's true, but the thing is that this is also the little span of the cycle. This is why I'm saying
The top of the bottom.
you have like things like 2, 1, 1, 1, 1, 1, 1. So
But it's linear combination.
it's linear combination.
Basic cycles.
Yes.
The bottom is linear combinations
Of
cycles of this form.
exactly of boundaries.
Is there a nice continuous formulation of this?
For general topological spaces, or
Or at whatever version gives you something nice.
no, I mean this is a version of in the continuous case. I think it would be singular homology, which is already pretty sophisticated because you look at all the paths in your manifolds and look at all the surfaces you can embed there and all their boundaries. But yeah, it works and it gives you the same answer. So this is Poincaré, I think. So no, I think singular homology should be. Yeah, much later. Yeah, Poincaré did it like this, and I think Eilenberg-MacLane or. Yeah, no, it took more time until people dared to do it with all the passes at once, all the continuous passes at once. Okay, so in particular, H1 is trivial when every cycle is a boundary of a surface. So no holes. This is the intuition you should have, that at the end what we get is that the higher dimensional of connectivity is having no holes. I don't want to have something like this. This cycle here is not a boundary of a surface. I have a hole here, and I can pass my hand in this triangle, and the cycle I get around my hand is not a boundary. So somehow H1 measures the number of holes.
It can be disconnected.
It could be disconnected, and then it would be the holes in all the components. It doesn't see somehow the connectedness. It only see holes. So this is one way. And remember, we have the other way. We have cohomology. So this again will be useful to understand cohomology. The first cohomology is the kernel of this is the map going from edge flow. This goes from edges to triangles, and the image of del 1 star will go from vertices to edges. Let's look at this. I don't have something clever to say about this. It means that whenever I sum, it's all the f such that when I sum over a triangle, then I should have sum 0. So I will write it like this. I'm going over a triangle. This is the integral along the boundary of a triangle, and I want it always to be 0. What happens here? So now look at this. We know that the kernel of the dual map is the Kirchhoff, which is the span of cycles, and I want to use this again. So this is, I look at span of cycles, and this is the dual, because it's the image of the dual map, so it's the orthogonal complement of the span of the cycles. But in order to be orthogonal, to be perpendicular to a span, you just need to be perpendicular to each of the elements. So it's just cycle, perpendicular to the cycle. So it means that whenever I do any closed path, it doesn't have to be around the triangle. I need the sum to be 0. So sum 0 along any path. So I will say this is now any path, any closed path, the integral. Like think about it as line integration. The line integral should be 0 around any closed path, and this is the line integral should be 0 around paths which surround triangles. So now if you have the background of physics, you will call these, I think, closed and exact. So a differential form or a function, if you're a physicist, you would say function. Closed, it means that if you integrate over a path which is contractible, so you have also the surface inside, the integral is 0. And exact, it means that you integrate over any closed path, the integral is 0. These are terms of physicists, but it's useful for us. So the more useful one is the exactness. So think about, you can forget about this one. The interesting one is the exact condition. So and the exact, okay, why is it important to us?
But still again, by duality, the dimension of the cohomology should also be the number of holes.
Yes. Oh, yeah. I should say. So for the homology, I just erased it. We had a measure for the number of holes. Again, if you come from physics, you see that this is also a measure for the numbers of holes, because you want to say, how can I have a form, how can I have a differential form whose integral is locally 0, but somehow there is some large path such that the integral is not 0. It means that I have some hole in the middle, and what this function really is, it tells me the winding number around this hole. But I think if you never saw this formulation, then it won't.
Fill the big path with small triangles and show that it's the same
Yes, yes. If all the little triangles have integral 0 at the boundary, then also the big one will have integral 0. If it doesn't, then it means that there is hole somewhere. Exactly. But as Avi said, yeah, again, you can work out some duality argument, which tells you that homology is isomorphic to cohomology, but this is not true at all now over other coefficients. In the dimension 0, it was true over any ring. Here, it's not true. You really have
Not true over finite fields.
finite fields, yes.
Yeah,
Yes.
The linear algebra is just linear algebra.
It's linear algebra, yeah, but you need to look over other rings to get the general picture.
For expansion in high dimensions, you
No,
need to look at
no.
higher. Yeah, so for
No.
our purposes, it's
No, yeah. I'm not going there. But I'm just saying you can't ignore this word.
I mean, Gaussian classes are tricky.
Yes.
Yeah, you can add a class to itself and get zero. So I think even Poincaré didn't do that.
Mm-hmm. You think? Okay. So this is the first homology and first cohomology, and we see that both of them measure somehow holes in the plane. And so this is topology, now geometry. The first Laplacian is, again, the going
By the
up.
way, the Hodge theorem, which I think is one of the theorem, only picks up, it doesn't pick up Gaussian.
No, yeah. I don't, yeah.
Gaussian is very hard to get. This is a serious point.
Yes,
One of duality.
yes. It won't come up in my talk, but you see it in other places. Like in Gill's work, you have the counting of hypertrees, you have the torsion playing a big part there.
So this is not from flows to flows.
So this is from flows to flows. I want to write it concretely. Let's see what happens here, like we did for graphs. So let's pick some values, some A, B, C, D, E. And I take the Laplacian. So first I need the co-boundary. So, and I have the triangle here. So this is A plus B minus C, right? Because it's A plus B, and C I'm crossing at the opposite direction. And here it's A plus D. Let's do it more different. A plus D plus E. And now the boundary. So for both of these, I will get A plus B minus C. And okay, let's do it like this. I'll put here B plus A minus C. Here it's C minus A minus B. And here it's A plus D plus E, A plus D plus E. Should have started with D plus E plus A, and here E plus D plus A. And here it's 2A plus B minus C plus D plus E. Okay, so what happened here? See that each of them got the original value, B, C, E, D, and here 2A, because this was adjacent to two triangle. So, so delta 1 of a form over some edge really starts with the degree of the edge. But what did it gather from around? So you see that signs, you have here signs. Why did I get here plus A but minus C? Because it's just because the orientation I picked here, but it was because this A agree with C. They both live in this vertex, but it doesn't agree with B. This one enters and this one goes out. This gives me what I was looking about A.
You're looking at the middle edge now.
I'm looking at the middle edge, yes. So this A it doesn't agree with B. This is why I have here plus. It does agree with C, which is why I have minus. and it does agree with D and E, which is why I have plus. So you see, you need to. So there is no orientation. This is the confusing part. At no point is there orientation of triangles, but when I pick a value, when I need to measure it on a value, then I need to say at which direction. So here I have minus, I call it also the neighboring edges, but neighboring here is it is oriented. So the edge E is neighbored with this E prime and with this E prime, with these directions. So every edge is neighbored with this one and with this one, going in this direction. So you think you can flip it around, but you cannot just, it's edges which share a triangle, but you need to look at the correct direction. This is the Laplacian. Pity that I wrote it in purple, you probably don't see. But do you see the Laplacian? Okay. And again, the spectrum is the interesting. The spectrum of my complex is the spectrum of the first Laplacian, but I don't want to look at the trivial zeros. So in dimension 0, the trivial zeros of the Laplacian were the constant because these are the one that came from here. Now it's the one which come from one dimension below. So which are the ones which come from one dimension below? We had it a moment ago. These are the exact ones. So I want to look at the exact, the orthogonal complement of the exact form, the forms which are the gradient of a function on the vertices. And this luckily has a nice interpretation. This is the Kirchhoff. The dual of the exact is exactly the Kirchhoff. So the spectrum of the Laplacian is the spectrum of the complex is the spectrum of the Laplacian on Kirchhoff forms which preserve energy at the vertex. And now, when it's 0 in the spectrum, so this is saying that the kernel of the first Laplacian strictly contained the exacts, right? So, but the kernel of the Laplacian is the kernel of the co-boundary, and the exact is the image of the first co-boundary. So again, it's if and only if the first cohomology is not trivial. So again, did you follow this? It's what we had there exactly, what we had for graphs exactly. The difference is, and this is why I wanted you to pay attention in graph. If you look at this Laplacian, which takes a function form, and then take the original value, times the degree, and then sum for all these neighbors the values, I think you would never give I don't have any simple argument why, if there is a function which this kills, and it's Kirchhoff, so it's locally preserving at the vertices, it means that there's somewhere a hole in the complex. It's not like in graphs that if you have this Laplacian, and you say that, if I have a function in the kernel of Laplacian, it means it's locally constant, but it also needs to be of some 0. So yeah, I have a locally constant function of some 0 exactly when the graph is disconnected. There you see everything directly. Here I don't have any intuition even why I have a function which this Laplacian kills, which is locally preserving in the sense of Kirchhoff, if and only if I have a hole. So this is why things are not as easy when you go high. You don't see directly why things are happening, but the good news is that everything works the same. So how much time do we have? 25 minutes. Okay. So again, I want to say that, 0 is in the spectrum if there are holes. So if the spectrum is far away from 0, what does it tell me? I have some large one connectivity. strong one connectivity. And
So even connectivity is it's not about just
No,
moving
it's-
between triangles.
no, no,
along
no.
their edges, right?
No, no,
You
no.
can do it even if they are whole.
Yes. Yeah.
Perhaps you could say one word about what the continuous, so you mentioned Chiga earlier,
Mm-hmm.
then of course the graph thing came after Chiga. So here we have a manifold. There's Hodge theorem. Hodge theorem gives you the homology in terms of the kernel of a Laplacian. Now you want to say something about a spectral gap implying something.
Yes.
What is it in the continuous case?
That's an excellent question. So,
Before you tell us it's
so the thing here is that it works the other way. So in geometry, there were Chigger inequalities first in Riemannian geometry, and then people took it into graph theory. And I'm going to show you a higher dimensional analog for Chigger in complexes, and only somewhere in the future will be the analog. It's still open.
Yeah, can't one triangle?
I mean, so
you
you
don't
don't
get
have you're not going to give us a geometric meaning in terms of cuts or something. You
No.
don't have a geometric interpretation.
No,
of
and-
spectral
and-
gap.
No, and I've asked a few geometers, and they all agree that it's an excellent question, and they don't have an answer. What is the analog of what I'm going to do now for geometry? Okay, so
By the way, Hodge never proved this theorem. I mean, Weil proved it.
no.
He gave very easy proof using this map and minimizing energy.
Oh, for the
That's
geometry.
the famous Weil lemma. That's what's proved.
Mhm.
Hodge theorem. Hodge never had it.
Mm-hmm. How did he get the credit? Okay, so when I say strong one connectedness is misleading, because this is really how topology is called, having no holes. It's not about connectedness. One connectedness is that you don't have holes in your manifold. So maybe
Zero homology is ordering connectedness.
the what?
The zero homology is still connected
Yes, yes.
in ordinary sense.
But I can do this for complexes which are disconnected and connected, and like they don't tell me anything one another, the zero cohomology and first cohomology. Okay, so what I'm going to do is define the following. Here's the Chigger constant of my triangle complex. I go over all the partitions. I partite the vertices to three disjoint parts. I look for every partition, so they need to be,
So this is too complex.
yeah, still too complex. But you'll see what happens in the general case. Non-empty parts, and I look at the number of triangles with one edge in A, one vertex in A, one vertex in B, and one vertex in C. And I multiply by n, which is the number of vertices. Somehow you need it. It's like a scaling factor. This is the correct scale of this quantity, and divide by the sizes.
So it's very similar to what we do in paper with Friedman.
With Friedman. Ah,
It's
the
a triangular form. you
Mhm.
apply- yeah,
yes,
you
yes,
apply
yes,
triangular
yes.
form.
And
Apply to this sense. So you can apply them to vectors. You're applying it. So you're talking about the expansion now, not the eigenvalue.
oh,
Right.
I
But
think-
eigenvalue is just multiply them by three vectors. Right? You take the triangular form and apply it to three unit vectors.
okay. I didn't.
Okay, yeah.
I didn't read the paper, so I try to understand if I'm repeating the work, and I got the impression that no, but maybe I did. It would be sad. So tell me in 20 minutes. It's not very sophisticated what I'm doing here. So this is the number of triangles with one vertex in A, B, C, and I divide by the sizes, and this is what we get. So the theorem is again the spectral gap of the complex bounds the Chigger constant from below, where maybe I didn't.
Sorry, this funny notation means disjoint union.
Yeah. Yes, yes. I thought it was somehow.
I just want to understand.
Okay, so where the spectral gap is the minimal eigenvalue. So the minimal non-trivial eigenvalues. So
Why do you have this factor of n then?
somehow
Normalize.
this is the scale of the
You
yeah.
don't have such a normalization in standard.
But you're going up one dimension.
No, you think about E
Oh.
A
Yeah, actually,
Oh, right.
A B over 8.
Right.
If you added here B, then you would
Right.
put this n.
It is larger than n over the sure.
Yeah. Yeah, you could also make this with only two of them and not n, and take the two smaller one, but
And this
it
is
just become
relatively
uglier.
simple, right?
This is super simple.
Because you compare this disjoint sets to what you get. I mean, there are special cases of applying it to arbitrary vectors. In the lambda, well, okay.
I don't know. I'll just show you. So this is the minimum of the spectrum of the first Laplacian restricted to Kirchhoff forms. How do we do this? Just yeah. So this is embarrassingly simple, but what?
Nothing is embarrassing.
It is, I think.
Did you understand what you did?
So I have some partition to A, B, and C, and I want to show that this lambda bounds from below this value for all the partitions, and then I get it for the minimum. And we look at this the following form, just going from A to B. So for any edge going from A to B, I put C here. For any edge going like this, I put here A in this direction, and any edge here, I'm putting here B, and I have lots of edges. Oh, yeah, I should have said in the beginning, this only works for the complete skeleton case. Yes, yeah. Oh, this is important. So I'm assuming here that the graph is a complete graph. So we have all the edges, only the triangles. You only play with the triangles. Next week I will do the general case, which is not.
So the graph, the one is the complete graph. The triangles can be added.
Yes, exactly. And this is super simple. The general case is harder, and this I'll do next week. So, but this is very, very simple. So all the edges here get B in this direction, all the edges here get C in that direction, all the edges here get A in this direction, and other edges get 0. So here I have some edge, it's 0. That's it. All the edges are either between inside or going between two of these. And we'll call this F. So first of all, F is Kirchhoff. If I look, for example, at some vertex from A, what does it have?
You called A both the value of the edge and
Oh, yeah, no, I didn't say it, but I want to say that, no, B is the size of B, yeah, I need this. You're right. And A is the size of A. So let's put it some V and say that this V is in A. So how?
This is a complete analog of what happens in the case of graphs, and you put the sizes of the two parts.
Yeah, yes. If you've seen the proof for graphs, you should be very familiar. So Kirchhoff means that the boundary vanishes. So what is the boundary of this flow at a vertex at A? I have here, at any vertex of A, I have C edges going out to C. Right, so here there are C edges going out to C, and it's each one of them I have B coming in, and here I have B edges going out to B, and at each of them I have C going out. So in total this is C times B plus B times minus C, so it's 0. And the same computation would be in B and C. So I can use this F, it's in Kirchhoff, and by Rayleigh, the spectral gap is smaller than or equal than the Rayleigh quotient. So here I need F to be in Kirchhoff because lambda is only for the spectrum over Kirchhoff forms. So now we need to compute both of them. So FF is going over all values, FV square. So this is the definition of the inner product. So for all the values at, oh yeah, something was wrong here. It's a form, it's a flow, yeah. Go over all the edges. So I have A times B edges going from A to B, and all of them have C. So A, B, C squared. And B, C, A squared, and A, C, B squared.
ACBM.
What?
That's ACBM.
Yes. So I get here A, C, A, B, C. I'm sorry. N. But you were very close. Okay. So this is the denominator. The numerator, now we use the adjointness. This is del 1 sub del 1. So this is, so I move this here, and this is the square of the yeah. And this is, you go over all the triangles and compute the value over this triangle squared. And now we need to look at, make the analysis.
From V to E.
From E to T.
C.
Yes, now I'm going from here to here. You're right. You're right. So how do triangle looks? So I have triangles who look like this, and then this is just the sum over the boundary of the triangle. So all edges here have 0. So a triangle like this gets 0. A triangle which looks like this gets here 0. Here it has B, and here it has B, also in this direction. So again, the sum is A plus B minus B. So it's again 0. And only the triangle that I'm interested in gets A plus B plus C in this direction, which is N. So what we get is exactly T. Oh, so I get the number of triangles, A, B, C, and square, right? Because this is still squared. And then this divided by this gives me the number of triangles. 1n cancels over A, B, C. So this is the proof. So
And you have a user type from the other side.
oh, okay. So this is the big question. I don't have, but it's obviously there. So I have like random examples, and you see that it should be close, but I don't have a proof. So
You use the complete skeleton that you have all the edges in order to construct F. I mean, you're using this one. So if you don't have them, the F has to be more complicated.
so this is what I thought, and this got me stuck for, I think, almost a year. And at the end, no, you need to use this exact F, but work harder at different point. I would.
By the way, this is not defined, this F, if you don't have all the edges.
No, just put C on the edges you have. Yes. So
H is 0 if you don't have all the edges.
No, no, no. I need to
Okay,
work a
we'll
little
see,
harder.
we'll see,
Yeah, we have another week to do this. So the problem is, yes, I use heavily the complete skeleton here, right, to do this game. To say that they cancel out and it's Kirchhoff. This will break in the general case, but this doesn't. I didn't use here the complete skeleton case. This still cancels over different triangles and is n over this triangle, but this form is not Kirchhoff. But at the end, you can understand when it is close enough to Kirchhoff so that you can pull an argument. So this is next week. We have more time now? 10 minutes. So the other thing I wanted to show, but it also I think take a bit more, is the mixing. So I will state the theorem, and I think we'll prove it next week. So if the spectrum of X is contained in some small interval, doesn't matter, but I want epsilon to be small. Then for any disjoint A, B, C, but not necessarily a partition here.
You want the pseudo-randomness.
Yes, yes.
That is what you expect.
Yes. So what I got here, okay, for a minute, what I got here is that if the spectral gap is large, then the Chigger expansion is also large. So, Peter, you ask if I have an inequality in the other direction because it should be much harder.
This is the expander mixing lemma.
Yes.
Analog of
Yes.
this
So
one.
wait for a moment with that one. Just to finish with the Chigger. So it's true that this is the easy part. This is the easy half of the Chigger. But the thing is, this is the useful part of the Chigger in terms of you want to build expanders, you want to construct complexes, use.
That's if you know something about lambda.
Yeah.
Yeah, but lambda is very, I mean, now you have number theory, representation theory, spectral theory, functional analysis, and at the end you get something combinatorial. So it's true that this is the easy part, and I'm very much interested in doing something at the other direction, but this also opens up nice question. So what I will do with next week is show what I get from this for Ramanujan complexes. So maybe this will interest you. So there are high-dimensional analogues of Ramanujan graphs, and then you can really compute spectral gaps and say something about the combinatorics. So, but this gives you something about partitions. It only
If you have homology with the jth degree, then you partition into
J plus 1, yeah. And the proof will be just the same. So if I have here a tetrahedra, if I have here A, B, C, D, then you would really, at all the triangles opposite to A, put A, all the triangles opposite to D, put D, so it cancels. So there's no surprises. It generalized nicely. And also, I think if you generalize it in the other direction to graphs, you'll get the standard proof for the Chigger. Okay, so this tells you about expansion along partitions. But what if we want a set which are not a partition? So this is the idea of pseudo-randomness. If I have any three sets, I want to say that the number of triangles going between them is more or less what I would expect in the random settings. And yeah, and I don't think this carries too high. I mean, it's weird that it doesn't, but it's somehow the existence of directions. These things cancel out. I mean, maybe if you started counting them with directions canceling out, then you would get a generalization, but it doesn't. It's not nice combinatorially. So what you get is that the number of triangles with a vertex in A, B, and C, its discrepancy has its deviation for what you would expect in random is bounded by this epsilon times. So it would be A, B, C 2/3. So for graphs, the expander mixing lemma says that the edges A, B are far from AB over N by epsilon square root of AB. So this is for graphs, this is for triangle complexes, and again, you have the generalization. So this, I think I will only, yeah, it takes a bit more to prove. So next week I will do the expansion mixing lemma. And also here, if you have a complete skeleton, then it's easier. If you don't have a complete skeleton, then you need much more work. And I try to do the trigger for the non-complete skeleton, which will give us something about Ramanujan complexes. So stick with us.
For this, the proof for the expander mixing lemma, you use the spectral decomposition. You use the main eigenvector, you subtract it from the matrix.
No, I think this is what you did, and here the composition is to Kirchhoff and exact. So yes, just to give a preview, this is what you get. This part comes from.
Yeah, no, there's a subspace.
Right.
There's a
Subspace on which
Yeah,
yeah,
exactly.
they may be not, the cohomology may be trivial.
Yeah, if the cohomology is trivial, then I don't get anything interesting because this epsilon would also be k. Yeah, this touches 0. So this part comes from the exact forms, and this part comes from the Kirchhoff. So this is why I thought it's different from your method, because you have one trivial eigenvalue. Yes.
All right.
Thank you. But you can ask also a question now, even.
You can ask also questions.
Yeah.
You have no questions, so it's locked, open.
So Peter, you were saying about an analog of this in Riemannian geometry. So Yair Minsky, Alex showed this in the geometry seminar in Yale, and Yair Minsky had some idea with flows, taking a manifold, partition it to 3 parts, and look at the flows which go through all of them and trying to bound it with the Laplacian on forms. But it's really, very open and very interesting. וואו.
מצוין, ממש
תודה רבה.
מצוין.
ממש הייתי לחוץ.
ממש תהיה לחוץ.
קהל חדש וזה.
מה? כן, אבל קהל אוהד.
ראית אותי בכנס לפני שבועיים.
כן,
אני לחוץ, אני לחוץ.
ראיתי אותך, שם היית אצלם, אבל זה לא הצעה, זה לא עבודה שלך, בדיוק, זה לא אותו דבר. אתה מרגיש כאילו אחר, נכון? מעולה.
תודה.
יש איזה, תגיד, מי שרוצה לקרוא לזה כחוץ מהתזה של...
אוי, רגע, עשיתי כאלה. וואי, שכחתי מזה.
תחלק אותם בפעם הבאה.
פעם הבאה. כן.
אני אגיד את המעיד.
אני גם צריך מעיד. תודה. האמת שזה ממש רציתי שזה יהיה... כאילו... איך הפסקתי לפחד
אני יכול לאמת את החלק ההתחלה של ההגדרות, אני אפילו יכול בזמות ללמד, אם לא בא לך לעשות את זה שוב.
זהו, זה מה שאמרתי לך, שאם... אתה לא צריך ללמד את זה, אבל כשאתה עושה לפלסיאן, כאילו...
נחמד להתחיל בהתחלה, כאילו, מי שלא ראה גרפים ואקספנדרים בחיים, כאילו, פשוט להראות להם איך שמראים את זה בדרך כלל.
אם אתה לא...
בלי לבחור אוריינטציה, ממש.
זהו, אם אתה...
לא צריך את זה בשביל
צריך את זה כשאתה עושה כזה, את כל הארגומנטים של להעביר. כשאתה רוצה לעבור...
לא, אפשר פשוט...
אם אתה לא עושה
לא
ארגומנטים
צריך
זה לעזור.
אפשר להראות את זה ככה, אפשר להראות את זה ישיר, זה לא כזה חשוב.
סבבה. פשוט ראיתי בקורס של נתי שהוא בחר כיוונים.
לא כתבתי ריקולקשן נוטס, ובשום מקום אין וידאתי מההתחלה לסוף שאין אוריינטציה.
אני ממש התווכחתי עם אנשים חכמים, כאילו הם מתחילים להסביר לי, לא, פה זה כן תלוי בכיוונים שבחרתי.
אני עכשיו גם עשיתי את הסוויץ' הזה, כאילו שנחשוב על זה בתור מוסלימות.
כן.
כאילו שתיים משול, כאילו עד למה שתיים.
ארבע אתה כבר...
וארבע זה כבר לא...
אבל הקטע זה שאתה באמת פשוט הולך מסביב למשולש, כי ברגע שאתה מסתכל בספרים, תמיד יקחו...
עכשיו אני כאילו ממש...
זה פלוס זה מינוס זה.
שאני יכול לחשוב על זה, כי אני מבין מה קורה.
לקח את הציון.
אני יש לי כבר ממש את הציון הזה, אני זוכר.
את כל הדברים ש...
כן, זה מעט כזה ש...
כן.
זה מקום שעושה Z1 למטה, במקום Z1 למעלה, וזה מה זה בלתי.
יכול שזה מאמר שלא שלחתי, אז...
אתה אומר משהו, Z1 למטה, אתה מתאר את זה במילים, ואתה מתאר את Z1 למעלה, וזה...
אז...
אני מנסה ללמוד את זה, כאילו...
תאמין לי שאני נתקעתי מספיק, זה נורא מעצבן, אתה לומד משהו, ברור שזה שגיאה מטופשת, אבל זה תוקע אותך שעות.
Thank you.
Thank you.